In this video, we will start our study of calculus by looking at something referred to as a limit. Now, what's interesting about calculus is, and as you go through your study of calculus, you'll come across certain key definitions, and all of those key definitions are expressed using what we call a limit, right? So it's important to understand, at least intuitively, what a limit is if you have any hope of being successful at understanding calculus and using calculus, right? So let's start by, let's say this. So consider a certain function f of x, and let's look at the function x cubed minus x squared plus 3x and then minus 3. Right, my exponent there doesn't look a lot like a 2, but let's make sure that you can see that that's a 2. And then that's all divided by the quantity x minus 1, right? So let's look at this function. So back in algebra, you would have studied the concept of the domain of a function, right? So let's ask ourselves this question. So what is the domain of f of x, right? So when you talk about the natural domain of a function, you're referring to all values of x for which f of x is defined. So that's kind of what the domain of a function is. So the domain is referring to all values of x, right? In this case, because that's our independent variable, for which f of x is, we say, well defined. Right? Well, what does that mean? It basically means all the values of x that we can plug into this function and get a number, right? Well, if you look at all the operations in this function, you can see the only time we would have any kind of problem is if we end up with a 0 in the denominator, right? So in other words, we could not substitute x equals 1 into this function and get a number. We couldn't get a y value, right? So how do we say that? So remember, there are different ways you can express the domain of a function. Let me just remind you of a few. So in this case, here's one way you could answer this question. You could say that x is not equal to 1, right? So you could say it like that. If you wanted to be a little bit more formal, you could use the set builder notation, that it's the set of all real numbers such that x is not equal to 1. If you wanted to use your interval notation, then it would be going from negative infinity up to 1, and then you put a parentheses there because you can't include the 1, and then union with the other interval 1 to infinity. You could do positive infinity if you wanted to be very precise. So you could do something like this. So there are lots of ways you can state this. All of these are acceptable ways, right? But what this basically means is we can plug any value of x into this function except 1, right? And get an answer. Answer meaning get a number. So like if we were trying to find ordered pairs, we would always find a corresponding y value for every x value except x equals 1, right? So that's the idea of the domain, right? Right? And so, in fact, let me say one more thing here. Another thing we could say is that f of x is not defined at x equals 1, right? It's not defined there, right? But let's ask ourselves, okay, so so that pretty much answers this question, right? We know the domain, we can plug any value of x in, and we can get a number out. But here's a follow-up question. So what? Let's answer this. So what happens to our function f of x as x gets close to x equals 1? So close to x equals 1. That's another question, and it's an equally important question, and it's going to get us closer to this concept of a limit. All right. So we know we can't substitute x equals 1 in, but what if we tried to substitute other values in? What would happen, right? And what do we mean by close, right? Well, think of your number line, right? So think of your number line like that. And think of 1, right? So we have negative infinity there, positive infinity there, and here is 1. Well, when you think of close to 1, you wouldn't think of like a million as being close to 1, or maybe 500 isn't very close to 1. It's far away from 1. But what are the numbers that are close? When you think of numbers that are close, you might think of numbers that are in an interval here, or maybe an even smaller interval here, or yet smaller interval there. That's what we mean by close, right? So what are some of those numbers? Well, something like maybe 0.9 is close to 1. And then if you wanted to get something a little bit closer, maybe 0.99. In fact, what we could do, we could actually make a table of values, and just choose some values of x that fit this idea of being close to 1, and then just plug them into our function and see what happens, right? We know we will get a y, right? We will always get an answer, because we're going to make sure that we don't choose 1, right? We're not going to choose this number, but we're going to choose values of x that are close to 1. So what would a table like that look like? Well, let me give an example of such a table. And let me scroll down here. Okay, so we're going to have x, and then we're going to have f of x. Okay, so here is the number 1. And I know I can't plug it in, right? So you can put like a dash there, or a null symbol. I'm just going to put a dash there to say, okay, I can't plug 1 in, right? But I can get close. So what I'm going to do is I'm going to start with the left side of the table first, and I'm going to plug values like this in it. Remember I said that 0.9 is close? Do that. And then what if I add another 9? Then I get a little bit closer. So instead of 9/10, maybe 99 hundredths. That's pretty close to 1, but I can get even closer. I could say, then I could use 999 thousandths, right? And then I can get even closer. I'm going to eventually run out of room in the table, but I can get pretty close, right, in a table like this. So it looks like that. So this is 9,999 10,000ths. So that's as far as our mind is concerned, that's pretty close to 1. All right. Now, again, this is where I will, in fact, let me do this. and just rewrite the function back here again. So you can see what we're going to plug in. And I will encourage you to verify the function evaluations, like all the function values that we're getting. Right? I will fill out the table, but you could even pause the video and try to evaluate this function at these 4 values of x, and then confirm that you get the values that I have. So if you plug 0.9 into this table, and what I'll do is I'll round the values in the table to 4 decimal places. Since the closest value of x that I have to 1 is to 4 decimal places, I'll put these function values, and you can think of them as y values as well. I'll round those values to 4 decimal places. All right. So when you plug 0.9 in, you'll get 3.81. If you plug 0.99 in, you'll get 3.9801. Let me make sure that you can see that decimal point. If you plug 0.999 in, you're going to get 3.9980. And then finally, if you plug 0.9999 in, you're going to get 3.9998. And you can probably see a pattern, right? You can see a pattern in terms of every time you add an additional 9 after the decimal point here in your x, you pick up an additional 9 after the decimal point here in your y value, right? Okay, so that's the left half of the table. Let's replicate something like that now, but instead of using values of x that are less than 1, and that's why I put these values of x on the left hand side of the table, because on my number line, values of x that are to the left of 1 are less than 1. So that's why I put these smaller values here, but they're getting closer and closer to 1. Now on this side, on the right side, I would have to use values of x that are bigger than 1. So I would have to do something like 1.1. Right, so I just go a little bit above. Just like down here, I started a little bit below. Over here, I'll start by being a little bit above. But I can make the numbers smaller. I can make sure that they're always bigger than 1, so they're always going to be on the right hand side here, but I can make them progressively smaller and smaller just by doing this, by doing something like this, 1.01 and then 1.001 and then 1.0001. And again, I could get even closer, but let's keep the table nice and balanced. I have 4 on this side. I'll have 4 on this side. What do I get when I plug 1.1 in? I get 4.21. What do I get when I plug 1.01 in? I get 4.021. What do I get if I plug 1.001 in? 1.001. I will get 4.0021. I'm sorry, 20. When you round it to 4 decimal places. That is a 0 there. And then finally, when you plug 1.00001 in, you will get 4.000, and you might guess 2, right? Okay, so that's our table, and we're gonna use this table to do a few things. One, we're gonna answer this question about what happens to f of x as x gets close to 1. And then I will tie that back into the concept of the limit and also introduce some notation, right? So based on this table, we are going to introduce some important concept, or a few important concepts, as well as the and some important notation. All right, so let's get to it. Let's take a look at the pattern that we see. So here, when x is less than 1, but is getting closer and closer to 1, look at the y values, right? These y values, as you look at them in this way, they are approaching 4, right? You got 3.81, 3.9801, 3.9980, 3.9998. So here, I'll just say f of x, the y values, right? So f of x approaches 4. It never gets there, right? Because we still have the 999. And again, if we had a big enough canvas and a big enough table, we could write lots of more decimal places after this, but it would never be equal to 4, right? Look at this side. Starting at the 4.21, 4.021, 4.0020, and then 4.0002. Again, going in this direction, right? Again, f of x approaches 4. Well, that's kind of interesting, right? From what we did earlier, we realized that we couldn't plug 1 into the function, right? Because 1 is not in its domain. We can't get a y value by plugging 1 in. But we could get pretty close to 1, and it seems like we would always get a y value. So let's write a couple things down and then translate it into symbols. So let's write it like this. So what I'm going to write now is going to describe the left side of the table. So as x is less than 1, right, and approaches 1, right, approaches 1, f of x approaches 4. All right, so we can write that sentence. And then similarly here, on this side, we could say, as x is greater than 1 and approaches 1, I didn't write it over here. F of x approaches 4. And then over here, I need a comma there. Gotta watch my grammar. F of x approaches 4, right? So we don't, in math, we love symbols, right? We love to be able to express things symbolically. It's like we have our own little language and we have our own little alphabet and syntax and everything. So I'm gonna explain how we transition from this statement to something that's more symbolic. So anytime, so like if we want to indicate that our x value approaches 1, right? We would do something like this. We would use, essentially, we're going to use the arrow, right, as far as our independent variable is concerned. We're going to use this right arrow here to say that it's approaching something. Well, what is it approaching? In this case, it's approaching 1, right? How do we indicate that, in this case, x is always less than 1? Well, what we do is, in terms of think of the 1 on the number line. Any value of x that's less than -1, I'm sorry, that is less than 1 would be to the left of 1. So we would put a little negative sign there to indicate that x is less than 1, and then the arrow is saying that x is getting closer and closer, right? So we would do this. And then what do we do about this part? Well, as far as the f of x approaches 4, right? This whole idea, it's not so much that we're going to use an arrow. We're only going to use the arrow for the independent variable. For the dependent variable now, when your dependent variable, in this case your y, when that approaches a number, we're going to say that that is represented by what we call a limit, right? So this would be the limit of f of x, right, would be, in this case, equal to 4, right? But what we need to do is to put these two things together. We need to put these two things together to tell us this entire statement. So this is what we do. We say the limit of, and I'll say it like this, the limit of f of x as x approaches 1, with that little negative sign there, that is equal to 4, right? And that's what the left side of this table is telling me, right? At least from a numerical standpoint, right? We're plugging numbers in and we're getting numbers out, and all those numbers right here are getting closer and closer to 4. This is how we would indicate that symbolically, right? Now over here, the only thing that is different is the inequality. This is where x is greater than 1. Everything else is the same. Approaches 1, when x is greater than 1 and approaches 1, your f of x still approaches 4, right? So what we need to do is to come up with a slightly different notation to indicate essentially what direction are we approaching x equals 1. Is it with values that are smaller than x or greater than x? Now, if they're greater than x, we need to change that minus sign to a plus. So in this case, we would do this, and it will be 1 plus. And when we put it all together, we would end up with this. So the limit of f of x as x approaches 1 plus, that is still equal to 4, and it's based on this, right? So that's what we mean by a limit. So let's kind of summarize this now. A limit, so now if in this case, when we specify the direction, right, we refer to it as a one-sided limit. So from one specific direction, if I plug values of x closer and closer to this number into my function, if I get a number out, right, we refer to this as a one-sided limit. So this is called a one-sided limit. And this one specifically, since the values of x are to the left, we refer to it as from the left, or a one-sided limit from the left. Over here, the only difference is we're now on the right side, like, because we're just slightly bigger than 1. So on the number line, right, slightly bigger than 1 means you're to the right of 1. So this is another one-sided limit, but from the left. So this is a one-sided limit, but specifically from the left. I'm sorry, from the right. Right. Now, when these two numbers are the same, so when the one-sided limit from the left is exactly the same as the one-sided limit from the right, we define the two-sided limit to be equal to that number, right? So if the limit, we'll just say this, from the left is equal to the limit from the right, we say the two-sided limit exists, and this is how we write it. So we say the two-sided limit exists, and we write this. So in this case, we would say the limit as x approaches 1 of f of x is equal to 4, right? So notice here, I didn't specify by using a minus or a plus. We basically say, regardless of the direction, right, that x gets closer and closer to 1, the function value gets closer and closer to 4. And it's that number 4 that is defined as the limit of this function, right? So even though, so here's another important thing that we can state. So even though f of 1, remember we saw this earlier, f of 1 does not exist, right? There is no function value. The limit as x approaches 1 of f of x does exist. And this is an important distinction to make, and it's an important, let me take this off, an important concept. So does exist, right? And it's, again, it's the difference between having a function value versus having a limit, right? So some important concepts here, and I just want to say one more thing before we end. This idea of using a table is helpful, but it's not efficient, right? You know, and this method here is basically called a numerical approach, right? You know, because, or tabular approach. And what you're doing is, again, you're looking for a certain pattern in the y values by using a certain pattern in your x values. But tables don't always work, right? So what we're going to rely on is we want a more precise way, if you will, and that's where algebra comes in, right? And we will revisit this particular function and look at it more from an algebraic standpoint in a previous video. But it's always a good starting point, you know, to like introduce the notation, introduce the concept, and then go a little bit deeper and try to be a lot more precise. So I look forward to seeing you in a previous video, or successive video, sorry.